bienvenidas al ciclo de seminarios del Instituto. Hoy tenemos el honor de recibir al doctor Bruno Sainz, que viene del Instituto de Investigación Ramón y Cajal, ITIS, y de la UAM, de la Universidad Autónoma de Madrid. El doctor Sainz es americano, aunque nacido en Madrid, naturalmente, pero él creció en Nueva Orleans y allí estudió su bachelor en la American University en Washington, D.C. E hizo el doctorado, no es lo que nos va a hablar hoy, sino en microbiología e inmunología en Tulane University. Luego realizó un primer postdoc en Scripps, en La Joya, donde trabajó en el equipo del doctor Francis Cisari, estudiando particularmente hepatitis C y hepatitis B, donde desarrolló allí un modelo de hepatitis C con el doctor Cisari. Y luego tuvo un segundo postdoc en la UIC, en la University of Illinois en Chicago, donde estuvo trabajando también en hepatitis C y publicó el descubrimiento de un receptor, el receptor de hepatitis C en Nature Medicine, y generaron un nuevo tratamiento, un nuevo medicamento para el tratamiento de la hepatitis C. Su vida cambió radicalmente cuando vino a España, a Madrid, al CENIO, donde ya no trabajó en hepatitis, sino que le ofrecieron un puesto para trabajar en células madre del cáncer, particularmente del cáncer de páncreas. Al frente del grupo estaba el doctor Christopher Hishing, y eso le ha ido llevando a cambiar con brillantez desde un campo de la virología, la microbiología, a un campo más de biología celular y molecular, en particular de las células madre del cáncer. Y he de decir que con gran éxito. Sus publicaciones están en los primeros niveles, ahora vais a poder comprobarlo. Están, además del Nature Medicine que os he dicho, en Cell Metabolism, en Cancer Cell, en Cancer Research, en GAT, que para los que trabajan en gastroenterología es probablemente la referencia por excelencia. Y en su etapa más reciente, desde 2014, tiene un puesto como Ramón y Cajal en el ITIS y en la Universidad Autónoma de Madrid. Y bueno, pues allí casualmente Raúl fue a dar un seminario, Raúl Luque, y contactó con él y vimos que tenemos intereses comunes. Hemos tenido una muy fructífera reunión esta mañana, hemos estado hablando de posibilidades de colaboración. Y quiero rescatar una idea que él me comunicaba hace un momento. Dice, cuando vine a España me di cuenta que aquí es fundamental colaborar. Y precisamente eso es lo que os quiero transmitir yo también a los más jóvenes que estáis estudiando el máster, que estáis haciendo el doctorado. Tenéis que tener los oídos muy abiertos, no solo a vuestro ámbito de trabajo, sino a mentes brillantes que hay en otros ámbitos de trabajo, en otras líneas de investigación, que es lo que os va a permitir crecer fundamentalmente. Vuestro ámbito lo conocéis bien, pero es muy importante que oigáis hablar de las células madre y eso os haga preguntaros si en vuestra patología, si en vuestra pregunta están también las células madre. Te agradezco mucho que estés con nosotros, Bruno, y bueno, estamos encantados de tenerte.
Muchas gracias, yo. So today I'm going to give a talk which I titled The Ever-Changing Landscape of Pancreatic Cancer Stem Cells. And I gave it this title because we discovered pancreatic cancer or cancer stem cells 20 years ago. And since then, the definition and how we view cancer stem cells has changed. So it's constantly changing. So I hope to show you today some advances that we've made in my laboratory in Madrid to further our understanding of these cells. And I think if I'm going to give a talk on cancer stem cells, I should give you all a brief introduction on what a cancer stem cell is. And when we talk about the cancer stem cell concept, we need to keep in mind that it's actually not a new concept. We officially isolated and discovered cancer stem cells in 1994, but even before then, literally in 1855 to 1975, there were multiple studies indicating that maybe cancer stem cells existed. And when we talk about cancer stem cells, we have to mention Rudolf Virchow, who we consider the grandfather of the cancer stem cell concept. He, along with Julius Cohnheim, proposed very early on that cancer was actually the development of, or came from the activation of dormant embryonic tissue. So there was even very early on connections between cancer and embryonic tissue. Since then, or since this concept or embryonal rest concept was proposed over a course of 100 years, we would learn about hematopoietic stem cells, and we would still continue to learn about the heterogeneity that exists between different compartments. Some further studies that led to the idea that maybe a cancer stem cell does exist, but it really wasn't until 1994 when Dick and colleagues showed for the first time that cancer stem cells existed because they were able to isolate these cells from acute myeloid leukemia. And it was a very elegant study at the time. It was published in 1994 in Nature, and all they did was a simple FACS sorting. They sorted out CD34 positive and CD34 negative cells and showed that the CD34 positive cells, when they injected these cells into immunocompromised mice, were the only cells that were able to form tumors. And they also showed that within this population of the CD34 positive cells, there's a CD38 negative population that also is tumorigenic. So there's also hierarchy within the cancer stem cell population. Now, since then, we've discovered cancer stem cells in just about all types of solid tumors. 2003 in breast cancer, and in 2007, Lee et al. And Herman et al. Showed the existence of cancer stem cells in pancreatic cancer, which is the tumor model we study in my laboratory. Now, the definition of cancer stem cell has constantly changed. Since 2006, we've in general used this definition, which is that a cancer stem cell is a cell within a tumor that possesses the capacity to self-renew and to cause heterogeneous lineages of cancer cells that comprise the tumor. So the tumor comes from the cancer stem cell, and only the cancer stem cell has the capacity to give rise to the other cells present within the tumor. This has been the concept that we've been following since 2006. Now, where are we today? Now we're in 2018, and what is our knowledge? What have we learned about cancer stem cells? Some people refer to them as cancer stem cells. I like to refer to them as stem-like cancer cells, but it's very difficult to publish that. Other people refer to them as tumor-initiating cells. What we do know is that these cells represent a very small population of rare cells within the tumor, and they have stem-like properties. And these cells are believed to be the cause or to drive tumor hierarchy, metastasis, resistance to therapy, which is very important, and of course, disease relapse. So these are the main characteristics when we talk about cancer stem cells. Now, I like to think of the cancer stem cell as the root, maybe the root of a tree, and all the rest of the tree comes from the cancer stem cell. So we can think of the cancer stem cell as giving rise to all the other cells within the tumor and then forming that hierarchy that we find within the tumor. So it's been considered a very unidirectional pattern. The cancer stem cell gives rise to the progenitor cells to more differentiated cells, and then more terminally differentiated cells within the tumor. And these cells would represent the bulk tumor cells, and the cancer stem cell would be the very small population within the tumor. Now, the cancer stem cell can do this because it can undergo both asymmetric and asymmetric division. A cancer stem cell can give rise to another cancer stem cell, or a cancer stem cell can give rise to a progenitor cell and all the other cells we find within the tumor. Only the cancer stem cell, in theory, can give rise to the heterogeneity we find within the tumor. And the cancer stem cell does this because we refer to it as a stem-like cell. It has stem-like properties, such as unlimited self-renewal, such as the activation of pathways that we usually find present in an embryonic or adult stem cells. For example, the activation of the Wnt signaling pathway, sonic hedgehog, Notch signaling. In pancreatic cancer, we also find activation of active and nodal signaling Hippo pathways. These are pathways we would normally find present or activated in stem cells. We also find these pathways activated in the cancer stem cell population. Now, I told you that our idea of cancer stem cells changes constantly. And last year, in 2017, two very important papers were published in using LGR5 positive cells in colon cancer, which changed our idea of the cancer stem cell population. So now when we talk about cancer stem cells, we have to talk about plasticity. And plasticity means that a cell, any cell within the tumor, can re-enter this differentiation process. And even a very differentiated cell can go back and become a cancer stem cell. While we always thought it was the cancer stem cell that gave rise to the differentiated cell, the path was very unidirectional, now we know that non-cancer stem cells can give rise to cancer stem cells. It's not very common. It happens when these cells receive the proper signals from the microenvironment, and it happens when we eliminate the cancer stem cell population. So we've thought for many years that if we eliminate the cancer stem cells, we'll cure cancer. But if you eliminate the cancer stem cells, the non-cancer stem cells can take their place. So this is something we need to keep in mind when we are developing therapies against different types of cancers. So now we know that there's a plasticity. So even terminally differentiated cells can give rise to cancer stem cells, and all of these cells within this hierarchy can give rise, if necessary, to a cancer stem cell. This has been shown in colon cancer. It's yet to be shown in pancreatic cancer, but there's no reason to think that it's not the same. So we know that cancer stem cells are a stem-like population. They drive tumor hierarchy, metastasis, chemoresistance, and disease relapse. And in theory, if we can target these cells and maybe target the cells that could become cancer stem cells, we could, therefore, in theory, this could result in tumor elimination. But for this, we need to accomplish three things. We need to first be able to identify and isolate these cells in order to study them. We need to understand better the biology behind these cells. What makes a cancer stem cell a cancer stem cell? And of course, we can never forget that in a petri dish, we have cells, but in the tumor, we have tumor cells and a microenvironment. So we should never forget about the microenvironment and the importance that the microenvironment has communicating with the cancer stem cell. So these are the three obstacles that we find in the cancer stem cell field, and three obstacles or three of our goals that we want to overcome and learn in order to learn more about the cancer stem cell. So in our laboratory, the way we work with cancer stem cells is we don't use established primary cell lines. In my personal opinion, established primary cell lines do not contain cancer stem cells, or if they do, it's a very small population. I think it's better when you want to study cancer stem cells from a tumor to use fresh tumor samples or PDX models. So in our laboratory, we have a very excellent collaborations with pathologists, surgeons, oncologists in different hospitals in Madrid, even hospitals in Germany and in Turkey, that we're able to get tumor pieces. We can take these tumor pieces and do a digestion straight from the tumor piece, pass it through a cytometer, and analyze the cancer stem cell population. We can do this by marking the cells after the digestion with different antibodies that can identify different receptors that have been described to be expressed on the surface of cancer stem cells. And here are just some examples: some prostate cancer, CD133, breast cancer, ALDH1, etc. These are different markers you can use to identify or to look at the cancer stem cell population within the tumor. If we're lucky enough and we have enough material, you can try to establish, in pancreatic cancer it's very difficult, but it's a bit easier in other types of tumors. You can establish an adherent culture. And then you can take this adherent culture and put it into what we call sphere culture. Differentiated cells in anchorage-independent conditions, and when you take away serum, will undergo apoptosis. Cells that have stem-like properties can survive without anchorage and without serum. So these cells, these cancer stem cells, can then give rise to these spheres, which is just an enrichment in cancer stem cells. It's not a full, pure population of cancer stem cells. Here we have just an enrichment of the cancer stem cells that were present in the monolayer culture. Since most of the tumor pieces we receive are quite small, we feel obligated to implant these tumor pieces inside or subcutaneously in immunocompromised mice, and nude mice, for example, which over the course of 6 to 8 months, these tumors can grow. Once the tumor reaches a sufficient size, we can extract this tumor, and then we can perform all of these assays to study the cancer stem cell population. This is generally what we do for pancreatic cancer. The benefit to doing this, although it is a selection process, the benefit is that we always have material that we can go back to. So we study, as I mentioned before, we study cancer stem cells in the context of pancreatic ductal adenocarcinoma, or PDAC. As you all know, it's a malignant neoplasm of the exocrine pancreas. It's the 4th most frequent cause of cancer-related death. It's proposed to become the 2nd most frequent cause by 2030. It's the deadliest form of cancer with a 5-year survival rate of less than 7%. And this is basically due to the fact that it's diagnosed at very late stages. Patients typically do not have symptoms, and when they do present, they already have metastases to other organs. So it's extremely metastatic tumor. It's also extremely radio and chemotherapy resistant. In our laboratory, we study pancreatic cancer stem cells. We try to isolate them using different markers. Some of the more established markers that we use are EpCAM, which is an epithelial marker, CD133, CD44, and CXCR4. These markers work. Are they specific for cancer stem cells? No. Do they also identify non-cancer stem cells? Yes. But these are just the challenges we have, and we have to accept some of the limitations of the assays that exist. So isolating cancer stem cells is not easy, it's difficult, and we do depend on the use of antibodies and on the use of sorters to be able to isolate these cells out of an in vitro culture or directly out of a tumor. So in 2011, we decided, could we improve on the ability to isolate cancer stem cells? And I have to give credit to the first author of this paper we published in 2014, Irene Miranda, who's a very talented graduate student in our laboratory who has now gone on to industry. She's actually working now for AbbVie, but she's an excellent graduate student. And I always tell the graduate students, you need to look at your cells. You don't just do assays, you don't just do Western blots, you don't just do qPCRs. It's very important to look at your cells to understand the systems you're working with. And she noticed one day in our cell cultures that we established from our PDX models, from the patient-derived xenografts, she noticed that some of the cells fluoresced green. These very small green punctate structures inside of the cells. And she noticed that when she put these cells into sphere cultures, and as I mentioned before, sphere cultures is a way to enrich for cancer stem cells, she also saw an enrichment in these green fluorescent cells. Of course, at first she thought she had contaminated her cells with GFP-positive cells. And when we looked at biconfocal microscopy, we saw that it was not the entire cell that was green. There were very small vesicles within the cells that were fluorescing green. And they had a very different emission and excitation spectrum from GFP. So it wasn't GFP, it was something completely different. The nice thing is, since it was fluorescent, we could track these cells by flow cytometry. So we could actually quantitate the percentage of cells within these adherent cultures. Here is adherent and here is sphere cultures. Here there are two tumors, PANC185 and PANC-JH029. And you can see that in adherent cultures, there's a low percentage of autofluorescent cells. And then in sphere cultures, we get an enrichment in what we called the autofluorescent cells. Now, she spent years, 4 years, trying to prove that these autofluorescent cells were indeed cancer stem cells. And I'm not going to show you all the experiments. I invite you to take a look at the paper. But the gold standard to show that a cell is a cancer stem cell is its ability to form tumors in immunocompromised mice at limiting dilutions. And what she did was limiting dilutions of these cells and showed in all cases that the autofluorescent positive cells, which I term here flow positive, from two different tumors were always the cells that outperformed the autofluorescent negative cells at the ability to form tumors. And in fact, we could get tumors from just injecting one single autofluorescent cell in immunocompromised mice. We went on to see whether or not we could also see these in other tumor entities. So we were also able to see the autofluorescent positive cells in hepatocellular carcinoma. Again, recapitulating some of the phenotypes, functional molecular phenotypes we had seen in pancreatic cancer. Also in colon cancer, we can identify autofluorescent positive cells and also inject those and show that they have high tumorigenic capacity. Now, obviously, we show this. We wanted to know what the autofluorescence was. Why are these vesicles being formed in the cancer stem cells, and what causes their formation? So we looked at many things. One of the things that caught our attention was the overexpression of the ABCG2 transporter. These are ATP-dependent transporters. We saw that they were overexpressed in the autofluorescent positive population at the level of mRNA, also at the level of protein. And we reasoned that while typically ABCG2 is expressed on the plasma membrane, ABCG2 could also be expressed on the membrane of these vesicles. The nice thing is that there's an inhibitor for ABCG2, which is FTC. And when we treated our cells with FTC for 72 hours, we saw that the autofluorescence disappeared. And when we removed the FTC and let the cells recover 72 hours later, the autofluorescence came back, which indicated to us that perhaps ABCG2 was on the surface of these autofluorescent vesicles. The most important experiment was to create a fusion protein or a vector that expressed ABCG2 fused to M cherry and see exactly where this ABCG2 co-localized or localized. And we saw that in the autofluorescent negative cells, you can appreciate here a little bit on the membrane, a lot in the cytoplasm, But in the autofluorescent positive cells, I hope you can appreciate that the membrane of the autofluorescent vesicle is covered in ABCG2, which is why FTC was a very good inhibitor of the accumulation of some product inside of this cell. Now, obviously, the next question is what's inside, what's giving it this green fluorescence? And to make a long story short, it's simply riboflavin. Riboflavin is a vitamin that if you dilute it in water, you subject it to UV light, is fluorescent. In fact, it makes sense because riboflavin is actually secreted into maternal milk by the mammary glands via ABCG2. So riboflavin can be transported across membranes via ABCG2, and what ABCG2 is doing here is concentrating riboflavin inside of the cells and giving us a new marker that we can use to identify and follow cancer stem cells. Now, since the publication of the paper and over the course of the last 2 years almost, we've established collaborations with hospitals in Madrid, for example, at el Hospital Universitario Infanta Sofia, with a group of oncologists, pathologists, surgeons, and what we've done is analyze now 92 different tumors to see whether or not other tumor entities also have autofluorescent positive cells. So literally taking the tumor, digesting it, and just seeing if we can detect autofluorescent positive cells. And what we found is that in the majority of the gastrointestinal tumors is where we are able to find autofluorescent positive cells. We have not seen it in prostate cancer, we have not seen it in breast cancer, nor in kidney or other types of non-GI tumors. And our workflow is just to take the tumor, digest the tumor, incubate it overnight with riboflavin. We do this just to enhance our capacity to identify the autofluorescent positive cells. If we give it more substance to concentrate inside the vesicle, then we can see these vesicles better. And the next day, we're able to see them by flow cytometry. This is just an example of a tumor freshly digested and incubated overnight with 10 micromolar or 30 micromolar of riboflavin. You can see very nicely the autofluorescent peak, which we're able to identify the autofluorescent positive cells. In some cases where we've been able to establish cultures from these cells, for example, this is patient 57, which is a rectum, and we're able to establish the monolayer culture, and also, if you can see here by fluorescence microscopy, the green punctate vesicles, which are found within this primary tumor culture. Again, we wanted to show that it is ABCG2, so we can treat these cultures with FTC, and you can see that the autofluorescence disappears, so it's the same autofluorescence that we were seeing in pancreatic cancer. And we can take these cells and actually inject them into animal models. We've established a fantastic collaboration with Laura Sánchez Piñón in la Universidad de Santiago de Compostela. She uses the zebrafish model as a model for sort of a PDX, a xenograft model for tumors of different types. And what we've done is inject our flow negative and flow autofluorescent positive cells that we isolate directly from some of these tumors into these zebrafish. We marked them previously with red so we can see that the injection was successful in both cases because these are negative and these are positive for autofluorescence. And you can see after 144 hours, these cells basically disappear. They're not able to maintain or exist within the zebrafish. And you can see the autofluorescent positive cells proliferate, and they can actually extend within the tail and extend within the zebrafish. So it's a very unique and very nice model. It's not the mouse, it's not human, but it's a very easy model to work with. You can do hundreds of fish at once instead of doing 30 or 40 mice, for example, in an experiment. So we're now also trying to use this platform to identify drugs that specifically eliminate the cancer stem cell population for personalized medicine with patients. But I think from our point of view, or our goal, basically, which was methods to identify and isolate cancer stem cells, I think we've made a great advancement in the cancer stem cell field using this marker. So I mentioned before, and I think what is most important is that we can isolate these cells, but we need to understand them. So we need to understand the biology behind them, what makes a cancer stem cell a cancer stem cell. And we've done many things to try to identify what we call the cancer stem cell molecular signature. You can do many assays, as most of you already know. Our interest was to see what makes a cancer stem cell different than a non-cancer stem cell, and what makes a cancer stem cell more like an embryonic stem cell. So what we did was isolate non-cancer stem cells using different methods. For example, you can culture them as monolayers. You can isolate them using autofluorescence. You can isolate them using the other markers that I mentioned before, such as CD133. You can do this the same for the cancer stem cell population, grow them as spheres. You can isolate the autofluorescent positive population, and you can perform a lot of assays. For example, you can look at the methylation profile So we reported doing a methylation profile on cancer stem cells and non-cancer stem cells. We actually discovered that the genome of cancer stem cells is hypermethylated. It's hypermethylated, and it's necessary to be hypermethylated in order to repress the expression of certain genes, in particular certain microRNAs that are anti-cancer stem cell. We've also performed microarray analyses to look at microRNAs that are differentially expressed in the cancer stem cell population versus the non-cancer stem cell population. And we've discovered, for example, this very interesting cluster, which is called the MIR1792 cluster. This cluster is not expressed in cancer stem cells because all of its targets are cancer stem cell important proteins, proteins that the cancer stem cell needs to be a cancer stem cell. And if you express this cluster, the microRNAs degrade those mRNAs. So the cancer stem cell does everything it can to make sure that this cluster is not expressed in the cancer stem cells. And we've also performed RNA-seq analysis. Obviously, the end result of all of these assays is to get a molecular signature or a list of genes that can tell us a little bit more about cancer stem cells. In our RNA-seq analyses, what we've seen is these are just 6 different PDX tumors. We've isolated the cancer stem cells from these tumors and the non-cancer stem cells, and we performed RNA-seq to see genes that are differentially expressed. So we can see thousands of genes that are overexpressed in cancer stem cells and thousands of genes that are underexpressed in cancer stem cells. And we've used this we've applied our RNA-seq data to different signatures. So we are interested in many things. We're interested in metabolism, we're interested in telomerase activity, we're interested in interferon signaling. So you can just basically get a list of genes and apply these genes to your RNA-seq data to see whether or not there's an enrichment in genes related to these signatures in cancer stem cells versus non-cancer stem cells. So we were interested in metabolism. We wanted to see whether or not there's a difference in the metabolic activity of cancer stem cells versus non-cancer stem cells. And this is a study we published a few years ago in cancers and cell metabolism. And what we saw is that in the cancer stem cell population, here on the right, is that we saw a list of genes that were overexpressed in the cancer stem cell population, which were not expressed in the non-cancer stem cell population, or less expressed. And these genes were involved in glycosylation, lipid metabolism, the Krebs cycle, the TCA cycle, oxidative phosphorylation, which would all indicate mitochondrial respiration. While in the non-cancer stem cells here, we found genes that are involved in glycolysis, pentose phosphate pathway, amino acid synthesis, and nucleotide synthesis. We validated these gene sets using arrays, PCR arrays, and we showed in here isolating cells by growing them as spheres, isolating cells, cancer stem cells by using the marker CD133. And we saw in all the cases we were able to validate our RNA-seq data. So it indicated that cancer stem cells might be using mitochondrial respiration to meet their energy needs. But this sort of goes against what we normally think about when we think about how cancer cells meet their energy requirements. When we think about cancer cells, we think of the Warburg effect. We think about glycolysis, that is the main route by which cancer cells meet their energy requirements. The Warburg effect is quite good. Glycolysis is very fast. You only produce 4 ATP molecules, or 4 ATPs per molecule of glucose, but it's a very fast process. So for a cell that needs a lot of energy, very quickly, glycolysis is very good. In fact, stem cells use glycolysis to meet their energy requirements, and only differentiated tissue, you can think of a hepatocyte, for example, use oxidative phosphorylation or mitochondrial respiration to meet their energy needs. It's a slower process, but it gives you 36 molecules of ATP per molecule of glucose. So obviously the question we asked is, do cancer stem cells meet their energy requirements via alternative pathways? And there's a very nice system called the Seahorse system, which actually allows you to measure the way a cell breathes, its ability to consume oxygen from the media. This is just a schematic of how you can interpret the data. You can measure the basal respiration that a cell has over the course of time. Basically, how much oxygen does it consume from the media? If it consumes a lot of oxygen and oxygen disappears from the medium, it's because it's using it, it's consuming it. Then you can add inhibitors, for example, oligomycin, which is an inhibitor of complex 5 of the electron transport chain. And what you do here, obviously, if you inhibit the electron transport chain, you're going to inhibit ATP production. You can uncouple the Krebs cycle, the TCA cycle, from the electron transport chain, also adding FCCP. And then this now, the oxygen consumption is not linked to electron transport, and now the cell you can measure the cell's maximal respiration. And you can add other inhibitors just to basically destroy every complex, and then basically the cell no longer is able to consume oxygen. So using this methodology, what we were able to show in this example, using CD133 positive cells and CD133 negative cells, we show that the cancer stem cells actually had a higher basal respiration and higher maximal respiration. This is just an example of one of the plots, and here's all the data across all of these different tumors where we showed that the cancer stem cells have a higher oxygen consumption rate than the non-cancer stem cells. This is from adherent spheres. This is from sorting using CD133 from cell culture, and this is sorting CD133 positive cells directly from a PDX tumor. So indeed, cancer stem cells uniquely meet their energy requirements via OXPHOS, via mitochondrial respiration, which is a process that I invite you also to take a look at the paper. This is mediated by a balance between c-MYC and PGC1 alpha. And we'll go into the details only to say that PGC1 alpha is very important for mitochondrial biogenesis, and MYC inhibits PGC1 alpha. So there's a balance in the cancer stem cell via expression of c-MYC and via expression of PGC1 alpha, which PGC1 alpha wins, and then now the cells can undergo biogenesis of mitochondria and can use their mitochondria to meet their energy requirements. So we've gone back to the RNA-seq. This is something we've been doing the past few years and try to find other pathways that are enriched in the cancer stem cells. So I'm going to show you now is unpublished data. These are data that we've been working on for the past 3 years, which we hope to submit very soon, but I think it's very interesting. I think it's also interesting if to always share with the public unpublished data as well as data we've already published. So when we went back to look at the cancer stem cells, other pathways that we found that were enriched in the cancer stem cell population was ubiquitin. So we found that the ubiquitin-mediated proteolysis was also enriched across all of the tumors that we looked at. This makes sense because obviously there's many papers published in many different cancers showing that ubiquitin pathway is deregulated in many different types of cancer. But apart from ubiquitin, there exist ubiquitin-like proteins or ubiquitin-like modifiers. Some of them you may know, you may have heard of. Sumo, for example, is a very common ubiquitin-like modifier. And there are other ubiquitin-like modifiers such as ISG15, NED8, and FAT10. ISG15 caught our attention. It caught my attention more than anything because it's involved in response to viral infections. And as Justo already told you, I've spent the majority of my career working on hepatitis C and on viral infections. And ISG15 is one of the proteins most activated when a cell is infected by a virus. And you can see here in our microarray analysis, or in our RNA-seq analysis, the heat map we generated, is many genes involved in an interferon response are upregulated in cancer stem cells, including ISG15 and many of the proteins involved in the ISG15 ubiquitin-like modification process. So ISG15, apart from being a gene that is upregulated interferon, it is a ubiquitin-like protein. Okay? It's called interferon-stimulated gene 15 because it was discovered first in viral infections and to be stimulated by interferon, but it is a ubiquitin-like protein, meaning that it also can conjugate. ISG15 can be conjugated to proteins just like ubiquitin, and this process is called ISG-ylation. So we have ubiquitination, we have sumolation, we also have ISG-ylation, we have NED-ylation, we have FAT-ylation, all these processes that can modulate post-translationally proteins, either target them for degradation or change their function. There's many ways to change the functions of cells. And you can see this in a standard Western blot. You can see the monomeric form of ISG15, and you can see the proteins that are ISG-elated. You just find bands. If anyone's ever done a Western blot for ubiquitin, you can see the same thing, ubiquitin monomeric and then ubiquitin bands in a Western blot. And you can see here, and when we compare adherent to spheres, so a culture enriched in cancer stem cells, our autofluorescent positive or negative population, or our CD133 positive versus CD133 negative population, we've seen enrichment in ISG-ylation and more monomeric ISG15. So ISG15 is very much like ubiquitin. It's larger, but you can superimpose these and you can see that's very much like ubiquitin. And also, like ubiquitin, uses 3 ligases, E1, E2, and E3, in order to ligate the monomeric ISG15 to its target protein here via lysine. And again, what we saw constantly is the enrichment of ISG-elated proteins and monomeric ISG15 in the cancer stem cell population. So obviously, before we ventured into studying whether or not ISG15 is important in pancreatic cancer stem cells, we looked at databases that were available, public databases, to see whether or not ISG15 is overexpressed in tumor versus normal tissue. We can see in all the databases that we looked at a very nice overexpression of ISG15 in tumors versus normal tissue. We also saw that if we separate patients based on the expression of ISG15, we see that ISG15 high patients have worse prognosis, worse overall survival versus ISG15 low patients. And we can go back to these databases. This is just an example of all of the patients within this database, their expression of ISG15. If we take the quartiles and perform GSEA analysis on this and look for pathways that are enriched, we found that in the ISG15 high patients, we also find an enrichment in oxidative phosphorylation, also an enrichment in mitochondrial respiration, which obviously caught our attention based on our previous studies in the cancer stem cell population, showing that they use mitochondrial respiration to meet their energy requirements. So we asked, is ISG15 involved in cancer stem cell mitochondrial respiration in OXPHOS? So first thing we did was to separate our cells. We separated them based on the expression of the autofluorescent phenotype that I showed you before, based on mitochondrial mass. So here in quadrant 3, what we have are the cells that express autofluorescence and also the cells that have the highest mitochondrial mass. And we actually isolated cells from these 4 quadrants. We performed a Western blot analysis, so we could see here that the double positive cells that refer to quadrant 3 are the ones that express ISG15. And at the level of RNA, so we perform RNA on these extracts, we can also see that these are the cells that overexpress ISG15 at the mRNA level. They express pluripotency-associated genes, which are related to stems, such as KLF4, and they also have very low levels of c-MYC. So I mentioned earlier this balance between c-MYC and PGC1 alpha. The lower the levels of c-MYC, the higher the levels of PGC1 alpha, and in theory, more mitochondria. So we proceeded to see whether or not this actually plays a role in pancreatic cancer. We established CRISPR cultures using CRISPR-Cas9 technology to eliminate ISG15, and then we isolated the mitochondria and the cytoplasm from our cultures. So we isolated the mitochondria from non-cancer stem cells, and we isolated the mitochondria from cancer stem cells, and also the cytoplasm from both. And we can see that, indeed, in the mitochondrial fraction, we find ISG, and we find ISG-related proteins. And in the CRISPR knockout, we do not see this phenotype, obviously, because we've eliminated the ISG15. So which led us to think maybe, indeed, ISG15 is somehow involved in stemness, in pancreatic stemness. So we developed, or we established more CRISPR-Cas9 cell lines where we basically knocked out ISG15 in 3 different new tumors, and we performed functional assays, which would be, for example, in this graph or in this panel, the formation of spheres. And you can see over primary, secondary, or tertiary spheres, these are generations of spheres, we see a reduction in the cell's capacity to form spheres. We do not, however, see a reduction in markers for cancer stem cells. So for example, this is CD133. You can see here these are our control samples. And then when we eliminate ISG15 using Cas9 CRISPR technology, we do not see a reduction in the CD133 positive population. So we are affecting stemness, but without eliminating the cancer stem cells. So the gold standard is to inject these cells into mice and see their tumorigenic capacity. Here we have our control cells that we've injected 10,000 and 1,000 cells in the tumors that are formed. When we use CRISPR-Cas9 to eliminate ISG15, we see an obvious reduction not only in tumor size, but also in the capacity to form tumors. And we can rescue these cells by overexpressing ISG15 as well. Here you see that the tumors formed here are not escape cells. These are not cells that still had a little bit of ISG15 and then were able to grow. These are cells, a different type of cell, maybe a different type of cancer stem cell that still gives rise to tumors. However, with 1,000 cells, these cells are no longer able to. And as I mentioned, we can rescue these cells by overexpressing ISG15 and then restoring the ability of these cells to form tumors. Just a summary of all the experiments we've done, we can see the efficiency in the absence of ISG15. With 1,000 cells, we have a 25% efficiency. We can rescue this, and obviously compared to the 100% efficiency of the control cells, it's a nice, very nice reduction. So we've started to investigate what is ISG15 doing in cancer stem cell biology. So again, going back to you should look at your cells. We're fortunate to have an electron microscopy facility at the university, and what we did is we went down to look at these cells. We thought maybe the connection with mitochondria, we would see less mitochondria in the ISG15 knockout cells. In fact, what we saw were more mitochondria. We saw more mitochondria visually. We saw more copies, mitochondrial DNA copies, when we eliminated ISG15. We saw more mitochondrial mass when we eliminated ISG15, here shown in blue compared to the red. And we actually saw also more mitochondrial membrane potential when we eliminated ISG15. So these cells have more mitochondria. They have a larger, more extensive mitochondrial network. Because we can't think of the mitochondria as very small organelles. They're not organelles. It's individual structures present within the cell. It's a very complex network. They're all connected. So we went to go back to the experiments that we'd done previously with the seahorse, and we saw that not only they have more mitochondrial, more membrane potential, they actually breathe more as well. Their basal respiration is much higher, which would make sense with the amount of mitochondria that they have. However, we saw that the maximal respiration was not very good. And we can take these analyses and you can do more in-depth analyses using, for example, here, spare respiratory capacity, maximal respiration, et cetera, and you can graph all of these different parameters of respiration. We can see that the basal respiration is higher when we eliminate ISG15. The maximal respiration is not any better. Proton leak is much higher. ATP production is not very good if you take in consideration the amount of mitochondria they have, the amount of mitochondrial DNA, and their spare respiratory capacity is very poor. So they're breathing, but their mitochondria are not very good at what they should be doing. And obviously, with this massive amount of protein leak, we know that when electrons reduce water from oxygen to water, you have many different products that are formed. Some of these products that are formed are, for example, the superoxide anions, hydrogen peroxide, hydroxyl radicals. A lot of ROS can be performed via electron transport chain or via mitochondrial respiration. And this increase in proton leak made us think that perhaps we were also having an increase in ROS. If we have an increase in ROS, that's bad. Normally cells that experience an increase in ROS can die, and that might be why ISG15 has a negative effect on the cancer stem cell population. So we looked at ROS production, and indeed, we have an increase in ROS using a probe called Mitosox, and we can see this here in the two PANC185 and PANC354. When we eliminate ISG15 via CRISPR-Cas9, we see an increase in ROS, but we do not see an increase in apoptosis. Absolutely no increase in apoptosis. We've never seen more cell death in the ISG15 CRISPR versus the control cells. So it's not the increased production in ROS, we think. So we went back to look at the cells again, and I don't know if you can appreciate from here, you can see here in the control cells, you can see visually you can see the crusts that are present in the mitochondria. And if you look at the mitochondria from the ISG15 CRISPR cells, a lot of them are actually empty, a lot of them lack crusts, which also indicate that they have a lot of mitochondria, but these mitochondria might not be very functional. And we know that when a cell has a non-functional mitochondria, what does it need to do? It has to eliminate it. And it has to eliminate it via a process called mitophagy. You have a normal healthy mitochondria. Over the course of time, all of our mitochondria become a bit unhealthy. They lose a bit of polarization. They start not functioning as well as they normally do, and they enter into an autophagic process, which is called mitophagy. Okay? This autophagic process consists of many proteins binding to the mitochondria. For example, PINK1. PINK1 will then phosphorylate parkin, and parkin will act as a ligase to ubiquitinate the mitochondria. When the mitochondria is ubiquitinated, it will then go into an autophagosome and it will be degraded. So this is a normal process of a mitochondria. All of our mitochondria are constantly being recycled. This is a normal part of biology. And we saw that if you inhibit mitophagy, there are many different inhibitors of mitophagy. One of them, for example, is cyclosporin A. You can see that when we inhibit mitophagy in control cells, we get an increase in mitochondria. This is just a marker for mitochondrial mass. This makes perfect sense. You inhibit mitophagy, you get now more staining of mitochondria. When we do the same experiment in the ISG15 CRISPR cells, we see we have no increase in the accumulation of mitochondria. In fact, cyclosporin A has no effect on these cells, indicating that there just simply is no mitophagy occurring in these cells. We've gone on to do further experiments. We can induce mitophagy with CCP. We can inhibit mitophagy with other inhibitors. And all these experiments, what they can lead you to is to determine what's called the mitophagic flux. This is the same thing you can do with autophagy. You can determine also the autophagic flux. And we can see that in the absence of ISG15, cells are just not capable of eliminating their non-functional mitochondria. So this is the model that we're working with. We know that a healthy mitochondria is also, it is ubiquitinated at times, and this ubiquitination is important to target it for degradation. We also know that mitochondria are also ISG-elated in cancer stem cells. And we believe that this ISG-elation is important at times. It's necessary to target these mitochondria because the cancer stem cell is using their mitochondria for ATP production. These mitochondria need to be targeted for degradation. Parkin has been shown recently to be ISG-elated. So if you cannot ISG-elate this protein, then you cannot finalize the mitophagic process. So you can have damaged mitochondria. These damaged mitochondria can produce ROS. We see that our cells do produce ROS. These damaged mitochondria need to go into an autophagosome, and we believe that ISG15 is important for this process. If we eliminate ISG15, then we don't get mitophagy. But we do get autophagy. We do see an increase in these structures that are very much related with autophagy. However, mitophagy is a process of autophagy. We can induce autophagy, but we just can't perform mitophagy. And we see this by our reduction in mitophagic flux. And of course, now we have a lot of mitochondria that are producing ROS. ROS is not killing our cells, but it's not to say that these cells might not be damaged in such a way that they can no longer form tumors, and we are inhibiting in some way the biology of the cancer stem cells. So this is just some data that I wanted to show you, showing how we've learned a little bit more about cancer stem cells at the level of their biology, particularly what their needs or what they use to meet their energy requirements. I'm not going to talk about the microenvironment. I just want to show you a quick cartoon just to give you an idea of the importance of the microenvironment. We don't know where pancreatic cancer comes from. We do know that pancreatic cancer is a dysregulation of microenvironmental factors. Inflammation, pancreatitis, is a driving force of the development of pancreatic cancer. We believe that there are mutations, or we know that there are mutations that are accumulated in cells. For example, KRAS mutations are present in 95% of pancreatic cancers. These can occur in ductal cells, acinar cells, dedifferentiated cells, centroacinar cells. The combination of these mutations and a dysregulation of the microenvironment then will give rise to the existence of a cancer stem cell. And this cancer stem cell will then give rise to all of the other cells present within the tumor. Now, the cancer stem cell is not alone, and the cancer cells are not alone. In pancreatic cancer, we have cancer-associated fibroblasts. We have pancreatic stellate cells, which are very important in communication, very important stromal cell also present in pancreatic cancer. We have immune cells, such as tumor-associated macrophages. We have secreted factors. And in the end, what we create is a very complex and dynamic microenvironment. All of these cells separately have their specific function, but we have to think of them in the context of the tumor. So within the tumor, they all communicate with one another. They communicate with the cancer stem cell as well. And this creates an important crosstalk, and it's a crosstalk that we've been trying to dissect in our laboratory over the course of the last 5 years. And we focus primarily on the tumor-associated macrophage. Primarily on this cell, because if you look at staining of PDAC tumors, and you can see the massive amount of stroma that's present within this tumor, very little epithelial cells are present within the pancreatic tumors, but one of the major infiltrating immune cell in pancreatic cancer is the tumor-associated macrophage. This is CD163. It's a marker commonly used for staining macrophages, particularly M2 macrophages. So we've been trying to find out why are there so many M2 macrophages within the PDAC tumor. Obviously, macrophages come in, they can migrate and infiltrate organs, tumors, etc. They're usually found in an activated pro-inflammatory form, which we can call M1 macrophages that express these markers. We can also find these cells because they're extremely plastic. We can find these cells also being M2 macrophages or alternatively activated or tumor-promoting macrophages that express these markers, and they can go back and forth. They can be an M1 today, an M2 tomorrow, and back to an M1. They're very plastic cells. But we find that in pancreatic cancer, there's a push to make these cells M2. And so we have a lot of tumor-associated macrophages that actually become friends of the tumor cells, friends of the cancer stem cells. And the cancer wants this because these tumor-associated macrophages can secrete many factors that actually promote tumor growth, they promote chemoresistance, and they also activate the cancer stem cell compartment. So I just wanted to mention or to emphasize also the importance of studying the tumor microenvironment when we want to study cancer stem cells. So in summary, I think this definition of a cancer stem cell is always changing. I think we need to add and think about the idea of plasticity more when we think about cancer stem cells. And we can't just target this cell. We actually need to target many of the cells within the tumor because many of them also have the capacity to turn into cancer stem cells. I think we've provided some interesting data to the pancreatic cancer field showing new markers to identify cancer stem cells. We've advanced our knowledge of the biology behind these cells. I think we are gaining a better understanding of the tumor microenvironment, especially tumor-associated macrophages, and hopefully all of this together will help us create new therapies, new strategies to eliminate these cells and the other cells that also play an important role in pancreatic cancer. So I just want to end by obviously acknowledging the people in my laboratory. These are the people in the laboratory that have provided data for the work that I presented today, especially Sonia Alcalá, who has been driving the ISG15 project. Our other collaborators, for example, past and current collaborators at the CNIO, Francisco Real, for example, Manuel Hidalgo, our clinical collaborators, Mert Erkin, Hannah Algul, Laura Sanchez Piñón at University of Santiago de Compostela, who has helped us develop the zebrafish model as an alternate xenograft model for pancreatic cancer. Our clinical collaborators, especially El Ramón y Cajal, Alfredo Carato, Julie Earle, and of course Laura García Bermejo. Paula Martinelli, who's helped us with a lot of the data set analyses and the RNA-seq analyses. And of course, I always have to acknowledge our funding sources because without them we wouldn't be able to perform our research, especially Carlos Tercero, Garantía Juvenil, ACC, and the Cancer Research Institute. And with that, I thank you very much for your time. I hope you've learned a little bit about cancer stem cells, opened up your mind about how important these cells are, and I'll be more than happy to take any questions. Thank you.
Thank you very much. Muchas gracias, Bruno. Podemos pasar, si queréis, al castellano en las preguntas. Y animo, como siempre, a los jóvenes a que preguntéis. Estoy seguro que nos ha interesado mucho a muchos de los que estamos aquí por la capacidad de estar en todos los tumores y de trasladar esto. Que algunos estaban con el teléfono mirando a ver si en tu tumor también había ISG15. ¿Preguntas? ¿Alguien rompe el juego? Carmen.
Gracias.
Quería preguntarle, en el orden de dibujar una terapia para ya que ha hablado tanto de la parte más biológica como de la parte independiente, ¿cuál es tu opinión sobre cómo generar, a qué dirigir la terapia más cómo dirigir la terapia más a buscar un gen como está explicando o una terapia que combine tanto la dirigirse a un gen muy específico como al microambiente al mismo tiempo?
Vale. Yo creo que hace mucho tiempo pensábamos que teníamos que eliminar simplemente la célula madre de cáncer. Y este estudio que mencioné, dos estudios que publicaron el año pasado en modelos de ratón, lo que hicieron a través de por un lado CRISPR-Cas9 y por otro lado utilizando una toxina, eliminaron todas las células que eran LGR5 positivas, que en cáncer de colon son las células madre cáncer. Y de repente lo que vieron es que desaparecía el tumor y a retirar el tratamiento volvieron las células STEM. Pero no porque no llegaron a eliminarlas desde el principio, las no STEM se convirtieron en STEM. Eso indica que simplemente utilizando un fármaco dirigido a una proteína o eliminando incluso fármacos que simplemente eliminan las células madre cáncer, con eso no vas a conseguir la eliminación del tumor. Obviamente lo que consiguieron manteniendo el tratamiento es una enfermedad controlable, ¿vale? Pero en el momento de retirar el fármaco o incluso si lo hubiesen dejado más tiempo, a lo mejor ocurren mutaciones y escape. Yo personalmente creo que el microambiente es bastante importante porque demostraron que la capacidad que tenían las células no STEM de convertirse en células STEM eran por las señales que recibieron del microambiente. El microambiente sabe cuando desaparecen las células madre de cáncer y mandan señales para que las no STEM se convierten en STEM. Entonces, estoy de acuerdo que lo que tenemos que hacer es como un cóctel, como un tratamiento como si fuese VIH, un cóctel que por un lado estamos atacando las células madre de cáncer, por otro lado estamos modulando de una forma el microambiente. Yo personalmente creo que tenemos que eliminar los macrófagos que están dentro del tumor. También los fibroblastos juegan un papel bastante importante, pero si tengo que elegir entre los dos, yo diría los macrófagos y también las otras células tumorales, porque con tiempo siguen proliferando, tienen la capacidad de formar una masa tumoral, a lo mejor no a largo plazo, porque eso viene de las células que tienen esta capacidad de proliferación sin límite, pero sí también tenemos que atacar esas células. Entonces yo estaría favoreciendo un tratamiento contra el microambiente, contra las células madre de cáncer y contra las células no madre de cáncer.
Y para usted precisar, y ha dicho que como elección personal preferiría un fármaco que eliminase los macrófagos, pero también ha puesto una imagen que, bueno, que más o menos tengo también reciente un poco el fibroblasto, el microambiente tumoral, la actuación sobre el fibroblasto, el mismo fibroblasto puede secretar y diferenciar los macrófagos, porque los macrófagos, es decir, el macrófago 1 es bueno, es que elimina tumor, y el macrófago 2 no.
Sí.
A lo mejor no sería mejor el fibroblasto, que es el que selecciona o que regula esa transición de M0 a M2, que es el malo, que favorece el tumor, ya nos va a atacar al fibroblasto que es el macrófago.
Puede ser, y yo creo que también eso tiene el contexto, a lo mejor va a ser diferente en cada tipo de tumor. Lo que no he mostrado hoy son los datos que tenemos nosotros eliminando los macrófagos y el efecto brutal que vemos. Utilizando pues diferentes fármacos, que es por ejemplo liposomas que comen los macrófagos y se explotan a través de apoptosis. Eliminando los macrófagos lo que consigues es, no tienes un gran efecto sobre tumorgénesis, pero sí tienes un efecto de casi eliminar metástasis en los ratones. Entonces los macrófagos son importantes, creo más que nada, en promover la expansión, la activación de las células madre de cáncer, ese cambio a un estado más mesenquimal, diseminación y metástasis. Entonces el hecho que en cáncer de páncreas metástasis es un problema bastante importante, por eso creo que el macrófago en cáncer de páncreas podría ser muy importante. Existen unos fármacos bastante interesantes para atacar, reeducar a los macrófagos. Eliminar el estroma es un poco complicado porque Tuveson ya mostró de forma muy bien en los ensayos de ratones, mostró que eliminando el estroma con inhibidores de Hedgehog conseguía que gemcitabina llegase mejor, eliminase las células tumorales. Cuando aplicaron ese fármaco a un ensayo clínico que fue súper rápido desde la publicación que tuvo Tuveson, al ensayo clínico era meses, porque pues era Tuveson y tenía unos datos brillantes en cáncer de páncreas, los pacientes se empezaron a morir. Incluso peor con los inhibidores de Hedgehog en cáncer de páncreas, mostrando que a lo mejor eliminando el estroma que está hecho por los fibroblastos no es buena idea. Entonces, hay que mantener el estroma, manipular las otras células que están aquí, pero obviamente esto es mucho más complejo. Yo te lo puedo dibujar muy bien con fibroblastos y macrófagos, pero la interacción, tenemos ahí también colágeno, tenemos las proteínas LOX que están haciendo muchas cosas. Entonces, habrá que modular, cambiar el microambiente, pero si tuviese que elegir una célula entre todas, pues para mí el macrófago. Pero eso no quiere decir que el fibroblasto tampoco no es importante.
Bueno, muchas gracias por la charla, la verdad que me ha gustado bastante.
Gracias.
Yo quería incidir un poco más en el concepto de plasticidad, en términos de, bueno, cuando desaparece esa cáncer stem cell, dices que digamos, las células yacentes son capaces de adquirir esa capacidad de stemness, sí, y malignizarse. ¿Vosotros en tumor sólido existen estudios de evolución clonal o de heterogeneidad de la cáncer stem cell?
Sí, sí.
¿Hay de eso al diagnóstico recaída, ver si no es que no somos capaces de detectar esa heterogeneidad? Y cuando un clon, nosotros vemos al diagnóstico un clon mayoritario, el clon que gana, que está en ese momento ganando la carrera de la leucemia, lo eliminamos con tratamiento si tenemos suerte, y otros clones minoritarios que no somos capaces de detectar técnicamente son los que ganan digamos que acceden a esa carrera de leucemia. En tumor, en páncreas pasa lo mismo.
Sí, sí, incluso hay un estudio, y se me escapa, se publicó en el 2017 en EMBO, y ya se me escapa el primer autor. Son un grupo que publicó ya en 2012 un estudio de lineage tracing en células humanas utilizando un estilo de códigos de barras, ¿no? Y lo que tenían una población de células, que cada célula tenía un código de barra diferente, y a través de PCR lo que podían ver son clones que a lo mejor por sistemas tradicionales como citometría no podemos detectar esas células, pero utilizando PCR para amplificar sí se podía ver. Y lo que vieron en cáncer de colon es poblaciones que existían en la primera formación del tumor, sacaban las células de ese tumor, lo pasaban a otro ratón, ahí estaban esos clones, lo pasaban a otro tumor, y de repente aparecían clones que no estaban presentes al principio. Y ya con más pases, incluso tratando con quimioterapia, aquí en este punto de la evolución, de repente aparece un clon que nunca ha estado presente. Saben que ha estado presente simplemente porque el código de barra estaba ahí desde el principio, ¿sabes? En el pool, pero de repente, después de mucho tiempo, aparece. Han hecho el mismo grupo un estudio muy parecido en cáncer de páncreas. Han visto cosas muy similares pero diferentes, es decir, que hay más plasticidad en cáncer de páncreas de lo que pensábamos, mucho más que comparado al cáncer de colon. Obviamente los ensayos de lineage tracing con color, con fluorescencia en ratones son muy bonitas y nos han demostrado muchísimo que existe esta plasticidad. Yo lo que no me gusta de la publicación de lo que os comenté en cáncer de colon es que dicen sin ninguna prueba que las no stem cells se convirtieron en stem cells, diciendo que la única población stem es las que expresan el GR5. ¿Vale? Pero a lo mejor hay otras células madre de cáncer que no expresan los marcadores que nosotros conocemos hasta hoy en día, que también pueden, en diferentes circunstancias, con tratamiento, eliminación de otras células que son importantes, activarse, que están ahí, siempre han estado ahí y son muy quiescentes,
sí,
no las podemos detectar.
El estado de precáncer está ahí.
Sí, y de repente dan lugar. No, es bastante complicado. E incluso podemos hacer cosas muy elegantes en ratones, pero es muy complicado hacer estos tipos de experimentos en muestras humanas.
Bueno, y una curiosidad, yo soy súper fan de la población, de un tipo de célula madre llamada Sainz population.
Sí.
He visto que la expresión de la BCG2 es bastante alta. ¿La habéis estudiado alguna vez, ese fenotipo?
Hemos visto, por ejemplo, en nuestra población de las células autofluorescentes positivas, vemos que aunque expresan a BCG2, no hemos visto nunca ninguna correlación con Sainz population y la población autofluorescente. También en nuestras líneas primarias que vienen de PDX, cuando sorteamos para Sainz population positiva y negativa, la positiva no es más agresiva que la negativa. Cuando utilizamos células ya en cultivo, que llevan muchos años en cultivo en el laboratorio, sí vemos diferencias. No, por eso quiero simplemente destacar que las células de ATCC o las que compramos para hacer estudios de STEM a lo mejor no es el modelo idóneo o correcto para estudiar células madre.
Y a lo mejor manteniéndola en dos dimensiones quizás pierdan.
Sí, ni he entrado en los modelos. Hay muchos modelos muy bonitos y muy buenos para modelos 3D, los organoides también, que son modelos bastante interesantes y bonitos para empezar a expandir y salir un poco del ratón, que también tiene muchas limitaciones. Y también empezar a estudiar otras cosas a otros niveles y otras dimensiones.
La última pregunta. Sí. La última. ¿Alguna más? ¿Alguna pregunta más? Si no, lo dejamos ahí.
Bueno, Bruno, te doy la enhorabuena, la charla ha sido impresionante.
Muchas gracias.
Yo tengo una curiosidad y una pregunta. La curiosidad es, no hemos hablado de recurrencia tumoral.
¿De la qué? Vale, sí.
Sí. No sé si hay recidiva en cáncer de páncreas, pero hay muchos tipos de tumores que sí tienen recidiva.
Sí.
Y leí hace años que había una controversia de si las recidivas venían de las cánceres stem cells que generaban de nuevo el tumor. Entonces hay algunos tipos de tumores en los cuales, hablando nosotros que tenemos mucha relación con los cirujanos, aseguran que siempre quitan el tumor.
Sí, sí. Por ejemplo, en mama
aparecen
puedes tener una cirugía fantástica, 8 o 10 años, que está el paciente sin tumor, sin metástasis, de repente ya después de 10 años, recaída.
Entonces, ¿cuál es tu opinión sobre el papel que tienen las cánceres stem cells en este tipo de...?
Vale, muy buena pregunta. Yo solo te puedo hablar de cáncer de páncreas porque ni soy oncólogo ni soy experto en cáncer de páncreas, yo solo lo hago como hobby. Lo que se ha descrito en modelos de ratón es incluso antes de la formación del tumor, utilizando modelos donde hay células marcadas con fluorescencia, antes de formar el tumor, ya estamos todavía en los estados de la formación de las lesiones neoplásticas, ya encuentran células fluorescentes en el hígado, en los pulmones y en otros sitios. Y se quedan ahí. Hay otros estudios que no voy a pretender a entenderlos muy bien, pero en cáncer de mama, que también haciendo estudios con células marcadas, encuentran células que se pueden quedar en la médula por mucho tiempo sin causar tumor. Si son células madre de cáncer, eso no te lo puedo decir porque esos estudios no hicieron una evaluación del estado STEM y yo tampoco no los he hecho. Teniendo en cuenta la definición de un cancer stem cell, yo diría que sí, son un tipo de cancer stem cell o un tipo de célula que puede con tiempo, en los momentos correctos, obtener propiedades STEM y de cancer stem cells y se puede dar lugar al tumor. Es interesante, los pacientes con cáncer de páncreas que tienen un tumor localizado y se puede intervenir con cirugía, quitar el tumor, una operación de 12 horas que se llama el Whipple, resectar el tumor y el paciente puede vivir, pero casi siempre hay recaída y por metástasis, indicando que estas células ya desde hace estados tempranos ya han salido a la circulación y ya están por ahí.
Entonces una buena opción terapéutica sería, como has dicho antes, que hay tratamientos que matan a las cánceres stem cell pero que muchas veces no son muy exitosos. Sería a pacientes a los que se les pueda quitar el tumor, aunque los cirujanos estén casi seguros que se le ha quitado el tumor, después tratarlos con este tipo de terapia. No sé si hay algún tipo de estudio, ¿no? Yo sé que la pregunta es complicada.
Yo desconozco simplemente por desconocer, a lo mejor existe uno. Yo no conozco ningún estudio que ha hecho un ensayo así. Obviamente las terapias de largo plazo contra las células madre cáncer es atacar vías que ya también están expresadas o activadas en células madre adultos. Entonces, ahí siempre vas a tener el problema que si a lo mejor un tratamiento de un mes o un par de meses para un paciente que tiene un cáncer es aguantable, pero un tratamiento por mucho tiempo a lo mejor sí puede afectar las células madre que tienen.
Última pregunta muy sencilla. ¿Habéis visto alguna relación entre el ISG-15 y el microambiente?
Sí.
Pero no lo has podido contar,
¿no? No lo he contado. Sí, pero sí, los macrófagos secretan IS-15 también. Para fomentar. Sí, para fomentar. Sí. Y lo estamos utilizando en Ramónica Hall para estratificar pacientes. Se encuentra bastante bien por el ISA en los pacientes.
¿Y en otros tipos de cáncer?
Otros tipos no sé. Vale, muchas gracias.
Muchísimas gracias de nuevo a todos.